Thank you for the kind introduction. It's a great pleasure for me to be here in sunny Stockholm today. So I will be talking today about generic problems of detecting communities and clustering of graphical data, which apply in many setups. But the primary application area that I'm interested in is that of online social networks. So let me show you as a starter, where is that? On the browser, an example of an epidemic propagation on Facebook. This is people reposting a silly picture on Facebook. So we see it's marvelous. It spreads everywhere. People are happy. They get access to this silly picture. And so information spreads. But the suspicion is that those online social networks can massively be improved. And in particular, I like to phrase it in terms of this so-called precision recall trade-off that people use in information retrieval. So precision is when what you see as data corresponds mostly to what you're interested in. And recall means that you don't miss much of what you're interested in. So if what you want is the yellow stuff, if what you see is the red stuff, you'd like everything to be orange somehow. And the suspicion is that in today's online social networks, there's poor precision and poor recall. We have lots of yellow and lots of red, and there's scope to make the two get closer. So this is the kind of application domain that I'm interested in. But as I said, clustering and community detection are very generic routines that you may want to perform in very different contexts. So, but the way we can use them in this context is to provide users with recommendations for new contacts, people who are of the same opinion or with similar tastes as they are, and that can help in collectively accessing, filtering the information that circulates. And you can also recommend directly content by figuring out that pieces of content are similar. So having accessed something, maybe you are primarily interested in similar things, and you can recommend content in that way. So community detection, if you think of users, it's about finding clusters of users who are like-minded, who have similar tastes. But if you think in terms of content, it's about finding communities of content items, of items which are similar. So this is what we want to do. We want to find groups of either users or content items that are similar. And so the mental picture one has in doing that is that there is a hidden topic space, you can say, that news items belong to, and so you observe a news item, and maybe it is somewhere in this topic space, and you'd like to retrieve this information to then recommend similar contents. And similarly for users, you may assume there is some hidden profile space, and similar people should be embedded at a similar location in the profile space. So we can either think in terms of clustering points of similar items, or embedding them in a space, in an embedding space, such that similar users are embedded nearby. And one basic example to illustrate what I want to talk about today is the Netflix dataset, which I assume many of you have heard of. So this is a big collection of ratings of movies by users, and it's basically a matrix, a sparse matrix, with rows for the users and columns for the movies. And if a user has rated a movie with a certain number of stars, you have that number in the corresponding entry. And so based on this kind of graphical data, we'd like to either embed movies and users in some space or cluster them in order to reveal the similarities. Right. So the roadmap for my talk is first to introduce the model, the generative model that I will be considering, which is a so-called stochastic block model. It has been introduced in the 80s, but we revisited it and added a twist with labels, which is motivated, for instance, by the Netflix dataset. And in this context, for this model, I would like to describe two kinds of results today. The first one is in a regime where we have a rich enough signal in the observation that allows us to do the clustering we want to do efficiently using a simple spectral clustering procedure. So I guess the spectral clustering is probably one of the most popular clustering techniques there are out there. But what is interesting in this context is that the analysis explains when it works. So this is more the analysis indicating the conditions under which it can work. That is the takeaway message here, rather than the algorithm itself, which is more classical. And then I will go to a second topic, which is still this problem of clustering in this context of the stochastic block model. But when the signal is not very rich, and here little is known. It's not a very well understood regime for this model. But I will describe some results and some phase transition phenomena that arise when we have a weak signal on which to perform the embedding and the clustering. All right, so let's get started. So the stochastic block model, this is the following thing. We have a large collection of items, could be either individuals or news items, let's say, or movies in the Netflix context. And we'll think of n as a parameter going to infinity. And we have a fixed number of categories or blocks into which these items are grouped. So k is that number, and this is to be thought as something fixed. And so we have a fraction of the total population that constitutes block k, and the size is alpha k times n. And then we have a random graph based on these groups of individuals, where we put an edge at random between two individuals with a probability that depends only on the underlying blocks of the users. So we have to specify the model, we just have a matrix B indexed by the categories. And so B sub k of u, k of v is the nominal probability of connecting an individual from a category, the first k, to the second k category. And the important thing is that we scale that. We have a 1 over n term, which somehow makes the total number on average of neighbors of someone of order 1 or of order b. B is something fixed. But we magnify that by this parameter s, which you should think of as the average degree in this random graph, or if you like, the signal strength. More edges will help you, and so the larger the S, the easier the clustering task will be. So that's the stochastic block model. That's it. That's very simple. And if you think of the adjacency matrix of this graph, the picture here reflects the expectation of this matrix, and it has this block structure reflecting the underlying blocks. And here, if you think of the Netflix dataset, you might imagine that you put on the first few blocks determine the users, the next blocks determine the items, and so we won't have edges between users and items, but this is something we can model in this framework. So that's the classical stochastic block model, and the twist is very simple. We just say, well, we may have more than just the presence of an edge. We may observe some additional information when we see some interaction between items. So the basic illustration is Netflix, where we see a rating, and the rating comes with a number of stars from 1 to 5. So we have a category attached to the rating. Another example might be if you have some partial observation of Facebook, you may observe whether or not a pair of individuals have exchanged messages or information in the past. And so we may see edges with a +1 or a -1, depending on whether an interaction has been seen or not. So this is a very natural twist to the original stochastic block model. Right, so what is spectral clustering? So this is, as I said, a classical method for doing clustering. You take the adjacency matrix. Let's forget about the labels for now. So you take this adjacency matrix A, you extract a few leading eigenvalues sorted by the magnitude of their absolute value. You extract the corresponding corresponding eigenvectors normalized, and this gives you an embedding at once, because you can then form a representative for each item, which is the vector of the components of the eigenvectors. So if we had R vectors of length n, and this, by transposing, this gives us n vectors of length r, and these are the spectral representatives of the users. Then we have this embedding, and the game is to show that this embedding reveals the hidden structure in the data. So for instance, for the sake of completeness, I described here one way of doing clustering in this spectral embedding. You could pick a typical distance, find a node which is surrounded by many neighbors at this typical distance, then magnify the ball and call that a cluster, and remove these nodes and carry on. So this is one simple-minded way of doing clustering, but there are many others. The important thing is more the embedding itself. So these are two illustrations of spectral clustering at work. On the left, this is the Netflix dataset, and taking the first two eigenvectors, we have a two-dimensional embedding, and the coloring corresponds to the so-called k-means way of grouping nodes. And on the right, this is synthetic data from the stochastic block model, where we have four colors corresponding to four clusters we have embedded in the model. All right, so what can we say about the performance of this kind of spectral embedding and subsequent clustering we can do in the spectral space? First, a result when we have a rich enough signal, and by rich enough, I'm assuming that if you like, the average degree in this random graph that we observe is of the order of the logarithm of the total population. The logarithm or larger. This is what we need. And I'm making an additional assumption about distinguishability. If I am to be able to tell apart two clusters, they need to have distinct statistics. So this is a very basic assumption. If it fails, then the two blocks should be thought of as a single block. So there's not much in this assumption. The key is more that we need some logarithmic scaling in the degree. And so the result we have in this setup is that the spectrum of the observed adjacency matrix, which is a noisy observation, is revealing the underlying structure in the following sense. We have a spectrum dominated by a few eigenvalues which are of magnitude S, this signal strength, and then the remainder of the spectrum is of order square root of S. So that's the first thing. So there's a neat separation between meaningful eigenvalues and noise when you do the spectral transformation. And moreover, the representatives of the points doing the embedding, if we pick the dimension correctly, will cluster around distinct points. So coming back to the previous picture, you should imagine that when the number S is large enough, the colored points get closer and closer to centers which are apart. So it's then very easy to tell apart the different clusters in that particular regime. So that's the result. And I will come back in a minute on the the arguments in the proof, because I think they are interesting in highlighting why spectral clustering can work. But before that, I will just return to this labeled model where we had added those extra informations by having categories indexing the edges. So if you want to apply spectral clustering, a simple-minded approach consists in sampling a random function from the labels to the reals between 0 and 1. So you just take IID random variables W of L for each potential label L. And using this, you can construct a matrix with entries that are no longer categorical labels, but numerical values by replacing the label L by the corresponding value that you've sampled W of L. And once you've done that, you just need to rephrase the separability assumption for being able to distinguish two clusters. But under the natural distinguishability assumption, you have the same result, namely for logarithmic degree, the spectral representatives cluster around distinct centers, and so you can easily tell apart which points constitute which clusters. For something a technicality, they cluster for all but a vanishing fraction of the points. So you may err on a few points, but most of them can be correctly clustered. So now here's an illustration of the application of this on the Netflix dataset. And so we embedded the users of the Netflix dataset into a spectral embedding, and we checked whether a user embedded that way would mark movies similarly as someone nearby in the spectral embedding. And so the x-axis is the proximity in spectral embedding to your neighbors. So you sort your neighbors from closer to further, and we plot the agreement probability. And so we see a baseline which is picking someone at random, which is low. But if we embed in, for instance, 30 dimensions is the green curve, the best one plotted here, we see that there is a stronger agreement between nearby nodes. So something has worked in this process of doing the spectral embedding. We have captured something about the Netflix dataset. So let's see now what goes in the proof of the result that for logarithmic signal strength, we can recover the clusters. So the first, there are two elements which put together give the result at once. The first result is one on random matrices and about the spectral radius of random matrices. So the topic of random matrices is quite well studied. There's an extensive literature on what people call Wigner matrices. So these are random symmetric matrices with IID entries. And so in particular, when they have moments that are well behaved, people have proven that the spectral radius of the matrix scales like the square root of the size, n, times the standard deviation of the entry, and they even know that there is a constant 2 in front, so this is a very sharp result. They have much more detailed information about that, about the dispersion around this leading contribution and so forth. But it turns out that we are not in this setup because we don't have well-behaved higher order moments. If you think about it, if you take the adjacency matrix of a random graph and you center it, what you have as entries are centered Bernoulli random variables. And so this is the matrix we would like to consider here. And the moments now don't scale like a power of the standard deviation. They blow up with n. N shows up. So we are not in this setup. But fortunately, sharper results applying in a broader, under a broader range of assumptions have been obtained in 2005. That's a paper by Uriel Feige and Ofek, where they show that, in fact, you don't need this strong assumption on the moments. What you need is, if you have centered Bernoulli random variables, you need their mean to be order log n over n, at least. So, and this is precisely where this log n comes from in the statement I was making. And if you have that, then the scaling for the spectral radius known in the classical setup, that is scaling like standard deviation times root n, still holds. The constant is no longer 2, but the magnitude is still correct. And so this applies to the stochastic block model. This can be applied to it, showing that if we center the random matrix by subtracting its expectation, then we have a spectral radius of order square root s with high probability. So that's the first ingredient. And the second one is to understand how addition of noise modifies the spectral characteristics of a matrix. And here there's a classical result about perturbation of the eigenvalues of a Hermitian matrix. If you have M as a Hermitian matrix to which you add a perturbation Hermitian matrix W, then the way you disturb the eigenvalues is bounded by the spectral radius of the noise. So we know about the spectral radius of the noise in our setup. And now we can use that. And this has a number of consequences. So if the matrix we are perturbing has well-separated eigenvalues, so delta is this separation, and the noise matrix has a spectral radius which is at most half this separation, then we can also relate not only the eigenvalues but the eigenvectors of the perturbed matrix to those of the unperturbed matrix. And specifically, to each eigenvector of the perturbed matrix, we can associate an eigenvector of the unperturbed matrix which is almost aligned. So we control the alignment using this Weil's inequality. We know that the scalar product is close to 1, and the proximity to 1 is given by this formula, and it depends on the ratio of the spectral radius of the noise to the gap between the eigenvalues of the original matrix. So these are the two ingredients, and once you have that, you can put them together. So in the context of the stochastic block model, we have the expected value of this adjacency matrix has blocks and has a very specific eigenstructure with a few eigenvalues of the order at most k, where k is the number of blocks. And these are determined, moreover, by the parameters of the model through a smaller matrix of size k by k. And so the spectrum of the expected value is precisely the spectrum of this small matrix magnified by the signal strength S, whereas we know by the result of random matrices that the spectral radius of the matrix after centering is of order square root S. So putting together these things with the argument by Weil's inequality, we know that the eigenvectors we use in order to construct the embedding are close to the eigenvectors of the expected matrix, which are constant on the blocks. And moreover, we can do a deterministic an analysis of the structure of this matrix. This is basic algebra, and we can tell that the corresponding points around which the spectral representatives cluster are distinct for different blocks. So that's it. So I think this is interesting to see that spectral clustering will work whenever you observe something that is a perturbation of a low-rank system, and that you have some tool to control the magnitude of the perturbation through its spectral radius. So this is basic, but this tells you a kind of setup where spectral clustering will work. So what I want to discuss now is what happens when the signal strength is not logarithmic. So we know things are easy in the case of a logarithmic signal strength. Now what about sub-logarithmic? So the weakest you might have is order 1. So let's say we have a matrix where the number of neighbors of each node is order 5 or 10, so small. In that setup, there is no hope to cluster correctly everyone if the data is originated by this stochastic block model, in particular because you have lots of isolated nodes in those random graphs. So when you see an isolated node, someone who has not rated anything, then you're at a loss. There's no way you can tell it's more similar to another one or not. So there's no hope to cluster almost everyone correctly, but you may hope to cluster correctly everyone who is connected. So in those random graphs, you have typically a regime where you have a giant component of size of order n, and this is what Erdős and Renyi, the pioneers of random graph theory, have shown in their first paper on the topic in '59. They have identified that in their random graph model, when the average degree is slightly above 1, then you have a giant component. So the hope is that you could categorize or cluster everyone who is reasonably well connected, so potentially everyone who is in this giant component of size of order n. And this formula for what I call the overlap is just a way of quantifying whether you have done a good job with a clustering rule. So a clustering rule k hat might be an assignment of a cluster number to a node, a particular node. And so the overlap metric will just tell you how many nodes you have correctly clustered. And I'm offsetting a parameter here just to avoid trivialities. If you decide that everyone belongs to cluster 1, then, of course, everyone in the biggest cluster will be grouped together. So this is useless, so it's just offsetting this. But, OK, so this is the setup. And what you would expect here is that the overlap becomes weaker and weaker, the one you can achieve through some method, maybe spectral, maybe otherwise. Until there is no longer any giant component. So this is the picture, the mental picture you may have, that there is a gradual decaying of what you can do, continuous and differentiable and whatnot in the signal strength. It turns out this is not like that. So this is what I want to describe now. You have another phase transition before the giant component disappears in those random graphs, where you cannot achieve a non-trivial overlap. There is no signal strong enough in your observation to allow you to say anything about the underlying block structure. And this is something that might be useful for two reasons. The first is if you have data that you can subsample, how far should you subsample? So this says there is a point below which you cannot subsample. If you go below this critical point, then the signal is useless. You have too little information to go about. And the other thing which is interesting in studying this phase transition, apart from the theoretical interest of it, is that if we can find a method that works right at the onset of the phase transition, whenever there is a very small exploitable signal, then this is probably a good method that might be robust and might do well even if we have more data. So these are the kinds of motivations for looking at these phase transition phenomena. So I will tell you a little bit more about the phase transition phenomenon and the few things we can prove on it, because unfortunately we cannot prove as much as we would like at this stage. So I will give you conjectures where I cannot prove anything. So I will consider a toy model, the simplest model of the labeled stochastic block model, where we have an illustration of that. And so this consists of two communities of equal size, and we have edge probabilities that are A over n internal to a community and B over n across community. So two parameters there for the connectivity, and then two distributions for the labels. Mu is the distribution for labels intra-community, and nu is the distribution across community. So this is a 4-parameter model, if you like. And so it turns out that on this toy model, we can compute explicitly this parameter tau, for which we can show that when it is less than 1, then definitely no method whatsoever will be able to achieve positive overlap. And this is not a result about computational power, it's a result about a lack of information present in the observation. Right, so it extends results that had been obtained by Mossel and Sly in a context without the labels. So they had precisely this tau, but the mu and the nu did not appear. And so we show that somehow this phase transition holds much more generally than was known. And on the positive side, we have something rather weak, but let me state it. When tau is larger than 1, there is this famous belief propagation approach to running some inference on a graph. And this belief propagation method has a property of being sensitive to noise, which I will explain in greater detail. And so this is not a strong statement, but it suggests that if you run belief propagation whenever you are above this threshold, then it is going to catch some signal. Right, and so this is an illustration of that. So simulations support this belief in belief propagation, if you like. So we have run belief propagation on many instances of the stochastic block model, varying critical parameters to go above or below the threshold. And the curves plot the overlap that we achieve. And indeed, we have as the vertical lines the predicted transition points. We see that positive overlap happens right after the transition point. All right, so let me tell you a few words about how those last two results are shown before concluding. So the first thing is that there is a random tree model that has the same statistics as the local neighborhood of the random graph in the limit of a large system. So if you have this random graph, you pick a node, it has few neighbors, you look at their neighbors, typically you won't have cycles. This is locally tree-like, and the statistics of those local tree approximations are easy enough to determine using Poisson approximation techniques. So we have these particular statistics. Each node has a number of neighbors that is Poisson. It has the same type its neighbors have the same type as itself with some probability, A over A plus B, and otherwise it's a flipped type between these two communities. And then the label is drawn according to the distribution mu or nu, according to whether they have the same labels or not. And so there is a seminal paper in 2000 by Evans, Perez et al., which considers a particular reconstruction problem on this kind of trees. Namely, it asks for the following question. If I have a tree with hidden states, those sigmas which say am I of community 1 or -1 with two communities. So the reconstruction problem on the tree is to ask the following. Can I guess better than randomly the type of the root node by observing the types of the nodes far away? So I have the tree, unfolding it, looking at the types of the leaves. Can I guess the type of the root by looking at the types of the leaves? And so they have developed tools to analyze these kinds of questions. And in particular, they provide tools for bounding how far off you are from, how better off you are compared to random guessing. So random guessing would be saying, well, my best estimate of the type at the root is 1/2. I don't know, asymptotically. If you can do strictly better than that, then you have managed to catch something about the state of the root. So they have those notions of capacities on the edges of those trees, and then if you have a non-vanishing capacity between the source node and the nodes far away, then you can do better than random, and this is what this formula says basically. And so you can apply that in this particular setup, and you will see that you cannot do better than random guessing if this critical parameter I was showing is less than 1. So this is one result. And then the second one is about belief propagation. So I think it's useful for those who are not familiar with it to just see what it looks like, belief propagation. So belief propagation is basically applying Bayes' formula, assuming some independence. So in this context, we again have this tree, so a root node I, and we have neighbors JKL, and they have downstream trees. And so belief propagation is a way of computing the probability of the type at the root node from the probabilities of the types at the neighbor nodes, forgetting about the root node, if you like, cutting off the root node from node J, say. And this is what this formula tells you, and it's basically Bayes' formula. So it's what is implemented in the belief propagation or message passing packages in machine learning libraries. So you just multiply some inputs corresponding to your neighbors, you normalize, and you have the characteristics of your node, and you can iterate that through message passing. So in the case of binary values, those you can take the ratio of the probability of a +1 to the probability of a -1, and this gives you a scalar recursions. And so what I was saying about the sensitivity to noise of belief propagation, now I can explain. So in this setup, trying to guess the type of the root node, you develop those equations, and you see that there is a fixed point which corresponds to the the complete absence of information. That is when the ratio of the +1 and -1 probability is 1. So that's a uniform distribution, and this is useless. So you would pass a message YY, which is 1 if your input messages were 1s, and so this is the useless fixed point. But the sensitivity to a perturbation of belief propagation is when by just moving slightly away from this useless fixed point, whether you are attracted back to it or whether you diverge away from it. And if you diverge away from it, this gives support to the fact that belief propagation will do something interesting, will not be trapped in a useless at a useless fixed point, but will instead go away and perhaps explore other parts of the state space and eventually converge to something that reveals the underlying structure. And so we can analyze whether this fixed point is stable or not, and maybe I will. Well, this is, I think I'm almost done after this slide. So we have, maybe I have not read that part on the previous slide, but we have this sensitivity of belief propagation, which we define as the variance of the message at the root node if we add slight random perturbations at the leaf nodes at some distance d. And we look at tiny perturbations. This is the meaning of this epsilon rescaling. And so if this k of d goes to 0 as the depth d goes to infinity, this is an indication of attractivity to this uninformative fixed point. And if it blows up, then this says that, on the contrary, you will be pushed away from the uninformative fixed point. And as I was saying, so the result is that this parameter tau predicts exactly when belief propagation is sensitive to noise. So above it, as we saw on the picture on the simulations, this property holds. So it's not a very strong result because we cannot prove what BP does on the graph models. We just know it does not get caught in this bad equilibrium. But the conjecture is that it does find some, it does converge to a meaningful other fixed point, which reveals some clustering with positive overlap. So this is a conjecture, and it seems hard. And actually, even asking whether any other method, not just belief propagation, not spectral methods, any method could achieve a positive overlap right above the threshold is still open and is apparently a hard problem. All right, so let me conclude. I think the first part on the decomposition between the perturbation results on the spectrum of matrices and the bounds on spectral radii of random matrices gives a simple way of understanding when spectral methods can work. Right now we are trying to push that to cases where we have not just a finite collection of blocks, but potentially an infinite collection of blocks, or even a continuum of types of nodes that we want to make sense of. Considering the second part, so we have numerical evidence, all kinds of indications that belief propagation is efficient in revealing the structure whenever there is structure to be revealed. But at this stage, this is still a conjecture. And so if you are interested in working on it, I'm happy to tell you what I cannot do and what seems possible as approaches to prove it. And with this, I will stop and take questions, if any.